Hello and welcome to my very first video of what will hopefully be a very long series. In this first video, I will start by looking at the definition of a meter and then looking at the definition of a kilogram. And then I'm going to talk about mass and comparing it to weight, which I think is a very important thing. Then we're going to look at base units, and then we're going to look at derived units, and we're going to finish the video by looking at dimensionless data. Please enjoy. Well, hi everybody. Welcome to the very first video of this series. And we're going to start today with length. This is a ruler and that is a meter. And we use meters, of course, all the time in science. Question: where does a meter come from? So if you go on the internet and look up what is a meter, it tells you that a meter is the distance that light travels in this tiny amount of time, because this 299,792,458 is the speed in meters per second of light, and therefore, by definition, 1 meter would be the distance it travels in that time. Now, that is a really terrible, useless definition of the meter. It is correct. It is scientifically correct because the speed of light is constant, and we now define length with reference to the speed of light. That's what we do in today's world. However, what originally was a meter hundreds of years ago in France? They had meters all the time. They'd have meters. People would buy cloth by the meter, and it was a standard sort of length. Meter in French literally means length, a length. And so what would happen is there would be, in different counties, in different towns, there would be on the wall a bronze or brass stick, and it would say, in this town, this is a meter, and people would compare to it. But there'd be different meters for different parts of the country. Not varying very much, but, no one could agree on exactly what it was. So, just around the time of the French Revolution, a bunch of very clever scientists decided that they were going to nail this once and for all. And what they wanted to do is they wanted to have a new system, and they wanted the meter, amongst other things, to be based on the size of something that did not change with time. They couldn't use a tree, they couldn't use a person. It had to be something that was pretty big and pretty obvious and never changed. So what did they use? They used the size of the Earth. Here's the Earth, North Pole, South Pole. And what they said was that they were going to measure very precisely how far it is from the North Pole to the equator in a straight line at sea level through Paris. So theoretically, this would be like digging a canal right through Europe, flooding it with seawater, and then going on a boat from the North Pole to the equator by boat down a canal that was dead straight. And they wanted to measure that distance. So they set off on an expedition. They couldn't measure from the North Pole to the equator because no one had any idea how to get to the North Pole in those days. North Pole exploration, another story for another day. And what they did was they actually only measured in a straight line from the coast, I believe near Ostend, and they measured a fairly straight line across France to somewhere near Barcelona in Spain. They measured that distance and then extrapolated with the size of the Earth, thinking how big the Earth was, how many degrees they'd covered, etc. And what they came up with was that they said the distance from the North Pole to the equator is, by definition, exactly 10 million meters, also known as 10,000 kilometers. So what they were saying was that the polar circumference all the way around was 40,000 kilometers, which also means that no 2 points on Earth in a straight line are more than 20,000 kilometers apart. So they did this, took them 4 years. They carefully measured the distance for this little bit across Europe. And then they came to a load of mathematics, and they came up with what they then called a meter. Now, very interestingly, so when they were measuring from across Europe, this bit here from the Channel down to Barcelona, complicated story, but basically they messed up a little bit and they didn't get it quite right. And if you want this distance to be a true 10,000 kilometers, you would have to take the meter that we have today, and if you add 2 sheets of A4 paper on the top, make it a tiny bit longer, that would then represent 1/10,000,000th of that distance. But it's not relevant, it's just where it comes from. So a meter was meant to be 1/10,000,000th of the distance from the North Pole to the equator in a straight line at sea level through Paris. And everybody said, hooray, that's the meter sorted out. But now they wanted a way of defining a mass that they had been using for many, many years, a kilogram. Now, a kilogram is a unit of mass, and mass is the amount of stuff in something. So this bag of sugar says 1 kilogram. It has a mass of 1 kilogram, and usually the way you would check it is to stick it on a balance, and the balance will say a kilogram. We'll come back to why balances are really lying to you later. So, how do you think, once they had got this, how did you get from the length of a meter to a kilogram bag of sugar? Well, this is what they did. They took their new super duper 1 meter and they made a box 10 centimeters by 10 by 10. And then they filled it with water. And they pointed at the amount of water in the box. And they said, lo, the mass of the water in the box is a kilogram. And so a kilogram is based upon the amount of water that they could put in what technically is called a cubic decimeter, a decimeter being a tenth of a meter. Okay, so 1 meter is 100 centimeters. 10 centimeters is also called a dm, a decimeter, and a decimeter cubed is basically a volume of a litre. It's also 1,000 centimeters cubed. It's also 1,000 millilitres. So 1,000 millilitres is the same as a litre, which is the same as 1,000 centimeters cubed, which is the same as dm cubed. And they all go back to being a box, 10 centimeters by 10 centimeters by 10 centimeters. Now, if you put water in a box, it is around a kilogram. But because the density of water varies with temperature, not by much, but by a tiny amount, it does depend on the temperature, depends on how much water you have in your box. Now, water is most dense at a temperature of about 4 Celsius. Now, that's another long story I'm going to talk about in the future, about why that's so important for life on Earth. But because it's most dense at 4 centimeters, they then decide to change the rules a little bit and say that a kilogram was a dm cubed of water at 4 degrees Celsius. And that was like that for about 50 years. And then they decided it wasn't really precise enough for them. So they then they changed the plan. And what they then did was they made a block of metal. I think it's from, oh goodness me, iridium platinum, I think. Very expensive metal. And this block of metal, I believe, this cuboid thing, it's circular when you look at it from the top, and from the sides, I think it was as tall as it was wide. And anyway, they made this very carefully, and they said that this is a kilogram, and that was called the standard kilogram. And for more than 100 years, a kilogram was defined by science as the amount of stuff in the standard kilogram sitting in Paris. And interestingly, different countries all over the world would have their own standard kilogram. And what would happen is they would take their standard kilogram, take it over to Paris, see if it was exactly the same, make sure it was exactly the same. And if it was, that's good. And if it wasn't, well, they'd have to adjust it because the one in Paris was always correct. Now, that, of course, leads to the interesting question, what would have happened if somebody had, say, broken in, stolen the standard kilogram? And you can imagine this on YouTube, right? There'd be somebody on YouTube with a stolen kilogram in one hand and a cheese grater in the other. And they'd say, give me millions of dollars, otherwise I'll make it less. And they'd start rubbing the standard kilogram. Because by definition, the kilogram would be changed by doing that. Now, in reality, even if somebody did that, it would not happen because scientists aren't stupid. They wouldn't say, oh no, we're going to have to change everything because somebody's used a cheese grater on it. They would simply use one of the backup standard ones, wouldn't they? Use a copy. But anyway, it's just an interesting idea. They kept this only up to about 5 years ago. And then 5 years ago, they had a complete rethink of all the units in physics and science, and they came up with another way of defining a kilogram. I'm not going to discuss with you how that works because it's very complicated. Maybe if we find time in a few years' time to talk about it then. But the definition of a kilogram now is really complicated, and you can look for it on the internet how they do it. In the old days, it was more simple. But the important point is that a kilogram is a measure of the amount of stuff inside something. So if I take my kilogram of sugar and I take this kilogram of sugar to the moon, is it still the same amount of stuff in the bag of sugar? Of course it is. If I take it to Neptune, is it the same amount of stuff in there? Yes, it is. Mass does not change. So, unless obviously I was to spoon some out on the way to Neptune and eat it or set fire to it or whatever, the amount of mass doesn't change depending on where you are. However, something does change, and that is, drumroll, the weight. The weight of an object is the force that the object feels because it's in a gravity field. Now, here on Earth, we have a gravity field, and that gravity field is causing this bag of sugar to be pulled down towards the centre of the Earth, and interestingly, there to be an equal and opposite force, which we'll talk about later, pulling the Earth up. The force on this bag of sugar is about 10 newtons. Its weight is about 10 newtons. We're going to be using, when we do our course, 9.81 newtons per kilogram for Earth, but we don't need to worry about that right now. What you need to know is the rules of weight and the rules of mass. And there are 3 key things about both mass and weight, which you've probably covered already, but we have to be completely straight on this. Otherwise, if you're starting for example, an IBDP course, you really have to know this stuff. Mass! It's the amount of stuff inside something. That will do. Doesn't need a fancy definition. It does not change. The amount of stuff does not change. And it's measured in kilograms, or grams, or tons, or micrograms, but it's basically based on the kilogram. Weight, on the other hand, is a force, and that force is due to a gravity field. We'll do fields much later. It is measured in newtons. Quick word on newtons. In science, the name of a person is capitalized. Mr. Newton, Sir Isaac Newton, would be a capital N for his name. However, when his name is used as the name of a unit, the unit is spelt with a lowercase. But just to confuse you, the symbol for the unit is usually a capital letter. So in this case, capital N means newtons, but it's always spelt lowercase. And it varies depending on the gravity field. So, for example, Earth, 9.81 newtons per kilogram, Moon, 1.6 newtons per kilogram. Okay, so how do we measure mass? Well, we cheat. The answer is this, that when I put my 1 kilogram of sugar onto some scales in the kitchen, and the scales read, oh, it's a kilogram, it's lying to you. Scales are basically a spring in there being pressed down by the weight and it makes a thing turn. It says, oh, it's 2 kilograms or whatever. Scales are lying. Do you think that a spring balance system can work out how much stuff is in this bag of sugar? Seriously? It can't. What it is doing is it's measuring the weight of the sugar. And because it knows, because we tell it, that we're on Earth, the weight of this bag of sugar inside the machine is about 20 newtons. And we say, if the weight's about 20 newtons, then it's 2 kilograms. Now, there is a way to work out its true mass, and that's basically by giving it a push and seeing how much it accelerates. We'll come to that later. That's Newton's second law. We'll cover that another time. All right, so I briefly talked about mass and length. And the way it works is that, now, again, it depends on the course you're doing. IBDP, we used to be very keen on you learning what I'm going to tell you. It seems to be with the new syllabus from 2023, a little bit less important, but for those of you that are doing A-levels, this is the important stuff and you need to know it. There are 7 what are called basic quantities, basic things that we have in science. And the first one is mass. And what this is the quantity, the base quantity is called mass. And the unit of mass, which is also a base unit, is the kilogram. Okay, so quantity mass, unit, kilogram. The next one we've done is length. And its unit is the meter for the meter. Now, I know what a lot of you are going to be saying. You're going to be saying, hang on. Why is it kilogram and not gram? Well, that's a very good question. Because it is. It just is, okay? I think because they decided, these guys 200 years ago, they decided that a gram was really too small to be a base unit, and they wanted it to be the kilogram. It's a very good point. You might argue it can't be the kilogram because it says 1,000 grams. It's a gram, the base unit. No, it isn't. But if you are sitting here doing chemistry, then it's a slightly different set of rules, because in chemistry, everything's done by the gram rather than the kilogram. But in physics, it's kilogram. So we have length and we have mass, and the third easy peasy one is time, and we will have lots of lessons on time coming up. And the unit of time, obviously, is s per second. What else have we got? Well, we've got a quantity. There's a quantity called the quantity of stuff, or the amount of stuff, which is really a bit weird. The name of the quantity is quantity, and its unit is the mole. And if you're doing chemistry, you'll be doing a lot of moles, and you've probably done moles before. A mole is simply a specific number of particles, and it represents usually 6.02 times 10 to the 23 particles or things. Temperature. Its unit is K, or Kelvin, and an individual Kelvin is the same as a Celsius. Again, we'll come to that later. Current in electricity, which we will cover in a few years' time, and the unit of current is the amp. There's not 6. There is, in fact, a 7th, the candela, which is to do with the amount of radiant energy from something, but that's never covered by anybody. You don't need to worry about candelas. You have to learn these 6, what we can call base quantities, and their base units. All other units in science are derived units, usually by either multiplying or dividing these things together. Do we have to learn these 6? Oh, yes, you do. All right, those 6 need to be learnt. Okay, so there are base units and from base quantities, and there are derived units and derived quantities. The derived quantity speed is such a simple one, and speed is simply how far you go in meters divided by how long it took you in terms of time, seconds, and we write speed as meters/s. And we have to have a conversation about the meaning of this symbol. Now, when you say it, you call it per, meters per second. What does it actually mean? It means exactly what it says on there. It's divided by. So the equation for speed is whatever the length is in meters divided by seconds, meters per second. However, you are now doing IBDP Physics, or you're doing some sort of A-level course, and we don't write speed as m/s anymore. You need to know this. This is a maths thing, not really a science thing. If I take something and I divide by s, it's the same as multiplying by the reciprocal. It's the same as meters times 1 over s. That's exactly the same as meters divided by s. And when I multiply by 1 over s, we can often say it's the same as being multiplied by s to the power of minus 1. S to the power of minus 1 is 1 over s. And so if, for example, so another derived unit, a common one that you've already encountered, would be density. Density is how much stuff there is in a unit-sized box. And the units are usually, and certainly in physics, are kilograms, the amount of stuff, per cubic meter box. And the symbol for density is that thing, not a P, it's a Greek letter rho. And this is also used a lot for different things in physics, very confusing, but there you go. That's a rho. Kilograms per cubic meter. It can also be written, and this is what you've got to realise, as kg m to the minus 3. When you were a kid at school and you were asked to do some simple stuff, we were measuring the length of something. And I don't know, there were different things. There was A and B and C thing and D thing. And you had to measure their length. Now, your teacher told you that you don't write centimetres in the box because you're supposed to write at the top. And you're supposed to do something like this, put it in brackets, length, centimetres, and if you did write cm, like that, you'd be told that's a terrible waste of time. But there's a reason for this. It's not just because it's a waste of time. It's because it's wrong. From now on, we aren't doing things with brackets. You will notice that in our books and in everything you see, at the top, it will say length, and it will then say something like that, the slash sign and cm. That means that it takes the length, 6.1 centimetres, and divides by centimetres. Huh? What do you mean, divide by centimetres? Well, what would be 6.1, let's do that, 6.1 centimetres divided by centimetres? What do you get? Well, the centimetres cancel. And you're left with a number, 6.1. This is called a dimensionless value. And, ready for this, every single table of data, every single graph that you encounter over the next few years is full of dimensionless data. It would be incorrect to say that 6.1 represents centimetres. It's not 6.1 centimetres. It's just the number 6.1. Obviously, it represents a length of 6.1 centimetres. We all understand it's meant to be something about length. Well, the number itself has had the length divided away, and you're left with just the number, 6.1, the value. Are we all cool with that? Okay, excellent. I think that's probably it for today. See you all next time. I will carry on general sort of stuff. Hope you found that useful. See you next time.